Hi everybody. I'm going to talk about baseband exploitation today, and mainly I'll talk about the Samsung Shannon baseband and how I was able to exploit it for mobile pwn2own last year in Tokyo. So this is the structure of the talk. Basically, I'll just give a brief introduction about me, and I'll also talk about some prior work that has been done for this on this topic. And basically, I'll give you a summary of what a cellular network is, because I'm pretty sure some people here don't know. And then we'll talk about the Shannon baseband and finding some bugs in it. And I'll do a demo, and it's a video. So my name is Amat Cama. Right now, I'm an independent security researcher. It basically means unemployed. But I play CTF with Shellfish, and my main focus is exploitation and reverse engineering. And currently, I'm focusing on hypervisors and basebands. And previously, I worked at Virtual Security Research, which is a pen testing company in Boston. Then I went to UCSB as a research assistant, but it was an internship. And I also worked for Qualcomm as a product security engineer, mainly focusing on Wi-Fi and Bluetooth. And then last year, I was in China for a few months working as a security researcher. And basically, we were focusing on pwn2own and things like that. All right, so about the prior work, I don't know if any of you has seen this talk, but it's pretty good, at least if you're interested in the Samsung baseband, because they really make the process easier by basically all the annoying work, they show you how to do it easily. So really, if you want to do some research on Samsung baseband, you should read this paper, and I mean, you should have a look at this talk. And I'm also going to be referring to it, because I won't be describing some of the things they already described in there. So why do we want to look at baseband? I guess because it's fun, first of all, and it's a unexplored area. I wouldn't say it's new, but it doesn't seem like there's a lot of research being done in there. And as a security researcher, unemployed one, you want to find some bugs. So if you know that nobody's looking over there, you want to, it's a good opportunity to find a lot of bugs and I guess learn a lot of things. Also, it has a pretty big impact, because I guess everybody here has a phone and it's connecting to some cellular network. So if you can find bugs in the baseband of different phones, then you can really attack a lot of people. And it just sounds cool to hack a phone by having it connect to a cellular network. So what is a cellular network? So it's basically just a mobile communication network. And the cells in the name is basically land areas, and they're covered by transceivers, base transceiver stations. And basically, they join different cells to cover a large area, and that's why it's called a cellular network. And technically, it could be any kind of network, but today we only talk about mobile phone networks, but there are other kinds of cellular networks. And I guess an interesting property is that you should be able to roam around the whole network without having to disconnect and reconnect every time you move from one cell to another. So I guess that's the whole purpose of this whole cellular network, kind of having all these different cells all working together to cover the whole country or whatever. So there are a bunch of technologies and standards that have been developed for the mobile phone networks. And I guess as time went on, people started requiring more and more throughput or faster speeds. And so basically, you have different generations that have been put forth. So let's have a look at those generations. So basically, there are two branches. the GSM branch and the CDMA branch. Actually, the CDMA branch was started by Qualcomm. And today we're only going to be talking about the GSM branch, but both of them share the LTE as the 4th generation. And the main differences are, I don't know if there are CDMA phones in the US, but in Europe, but generally those phones don't have SIM cards. So if you have a phone that works without a SIM card, it's a CDMA one. And yeah, I guess that's all about that. So there's this collaboration called the 3GPP, and they are the ones that are in charge of, developing and maintaining the technical standards, which are actually the documents describing how the protocols work in depth. So you have one for GSM, GPRS, UMTS, LTE, and there are bodies in there such as the ETSI, the European Telecommunications Standards Institute, and there's a bunch of other countries that have their own bodies inside. And I guess the technical standards, we care about them because we get in-depth information about what the protocols look like. So I have this scary looking diagram for you, but you should worry about it because, another something I have to say is this diagram is pretty wrong, but we don't care about that because basically it only shows what we're interested in as researchers if we want to find bugs, but normally it should be much more complicated than that. But basically what I want you guys to understand here is that from GSM to LTE, meaning 2G to 4G, the stack is kind of similar and nothing prevents them from working between each other. Just that I guess they've been improved. One generation improves on the previous one by adding new protocols and stuff like that. And basically, you see that GPRS is pretty much the same as GSM on the 3rd layer, except that the connection management has been changed to session management, meaning that instead of we're going from circuit switched network to like a packet switch network. And by that, I mean packet switch is basically now phones communicate by sending packets to each other, and the address destination is inside the packet, whereas when it was a circuit switch, it's just the phones were linked from one phone to another. So what is the baseband? I guess we want to talk about the baseband because that's what we're going to be looking at. And it's basically the component of the phone that handles communicating with the mobile network. I guess really is the phone part of the phone, because nowadays, we have all these browsers and stuff which aren't really needed for a phone to work. So it deals with the low-level radio signaling and all those things, and it supports all the standards we talked about. I guess it depends on the phone you buy, but let's just say they all support all these standards. So there are a number of different implementations. Qualcomm owns most of the market. So basically, as you can see, this huge list of phones, and most of them are using Qualcomm phones. So I guess one thing to point out is you see Galaxy under Samsung and Qualcomm. The difference is that the US Samsung Galaxy phones are using this Qualcomm baseband, while the rest of the world is pretty much using the one from Samsung. And nowadays there's the new Intel. I don't know if it's new, but at least it has just been recently started being used in phones, so such as the iPhone X, iPhone 8. And also there's Huawei, and I don't know how long their baseband has been around, but they also started using their own instead of Qualcomm. It used to be that pretty much all these phones used to use Qualcomm basebands, but now it seems like they started shifting towards their own, perhaps just to cut costs. So the most common architecture today is like this. So you have a chip that's dedicated for the baseband, and then you have another one, which is the application processor. So we differentiate between the cellular processor and the application processor. But it seems like in the past, it used to be that it would be just one processor doing both. And in that case, it would be interesting because if you own the baseband, it means you directly own the phone. So the code is generally written in C, C++, which is a good thing for us as researchers. And another thing is there's a communication interface between the cellular processor and the application processor. And usually they'll be like a serial link, you know, and also they use shared memory for transferring large amounts of data. Okay, so like I said, you know, because of this architecture, getting code execution on the cellular processor doesn't mean you own the entire phone, you know, the whole device. But still, a number of attacks can be performed. You know, you can redirect phone calls, redirect SMS, or modify internet traffic. And I guess modifying internet traffic can also mean injecting exploits for browsers or something. And a step further you can take it is you can attack the application processor through those IPC mechanisms. So now let's talk about the Shannon baseband. So this is Samsung's implementation, typically ships with phones featuring the Exynos SoC. And like I said, it's most non-Galaxy phones or basically most Samsung phones that aren't US based, and it's a real-time operating system running on an ARM Cortex R7. At least in recent phones, it's a R7. I guess it used to be R4 a while ago. So what's interesting, I guess, before we can do the research is obtaining the code. So luckily for us, it's not that hard. So the firmware in the Android firmware images, there's the modem binary, but it's actually encrypted. So, and I don't know of any easy way to decrypt that, but at least we can generate RAM dumps from the phone directly in order to get the code that's already decrypted in memory. So what it looks like is you just use this special code. It works on pretty much all Samsung devices. And this is what the menu looks like. So first we want to turn on, let me see if I can. Okay. So first we want to turn on RAM logging, and then we can enable debugging, the debug levels to make it, you know, spew more information, and then run CP forced crash dump. Basically, this will cause the modem to crash and generate a RAM dump. And after that, we can click on this copy to SD card, which actually makes the RAM dump available to us. And yeah, that's pretty much it. So this is a slide with a lot of text. Basically, it just describes what I just said. So we'll just skip it. And after the modem crashes, this is what you get. So first you get this pop-up menu telling you, you know, modem crash, doing RAM dump, and you gotta wait about 10 minutes. So basically every time you crash the modem, you're gonna have to wait. So really you should only try to make it crash when you're sure, you know, that you're gonna get something good out of it, because it's pretty annoying to wait all that time. And once the phone turns off, you get to this weird screen, which is the crash upload mode. I don't really know what it does. I guess this is probably they must have some proprietary way of communicating with the phone when it's in this state. But once it reaches this state, all you have to do is turn off the phone again and then boot it back to the normal interface. So, okay, now that we've got the RAM dump, we want to load it in IDA. So there is the CP boot daemon, which is part of the file system. Basically, it handles powering on the modem and processing RAM dumps, amongst other things. And by reversing it, we can see how it processes the RAM dumps it receives from the modem. And this way we can know how to translate this huge RAM dump file we get to actual virtual addresses in IDA, because otherwise the disassembly won't be right. And this is described in the talk I mentioned earlier, the breaking band talk. And they also provide a script to load in IDA. I mean, they provide one for Galaxy S6, but it's easily changeable to work for the S8. So now that we have the code loaded in IDA, and we know this is a real-time operating system, we basically want to identify the different tasks that the operating system runs. And we can start by reversing from the reset handler, which is basically the very first part of the code. And after a while, we'll end up seeing that there is a linked list that contains all the tasks that the OS runs. So, you know, it describes, it got a name for the task, it's got the entry point, the stack frames, and stuff like that. And by traversing this list, we can just list all the tasks, and the names of the different tasks are pretty useful in reversing. And these are examples of what they look like. So I don't know if you remember that diagram I showed earlier, but there's MM, which is mobility management, which is part of the third layer of GSM. And there's other things here that are interesting, like CC is also part of the third layer of GSM, and SM is part of the third layer of GPRS. So just the task names allow us to know that, oh, we don't have to reverse the whole 30 megabytes of code and start looking in those areas. So what are these tasks? What do they look like? So different tasks are used for different components, you know, different layers and protocol stacks. And the tasks communicate with each other using a mailbox system. Basically, all the tasks are loops, and they're checking their mailbox all the time to make sure that, you know, to check if there's a message. And if they pop one message out of the mailbox, they'll process it, and sometimes they'll end up sending a message to another task through that task's mailbox. So I guess this is a very, very simple design. So maybe it's standard for all RTOSs. I guess actually it is, because I remember looking at Huawei and they're using a similar design. So basically you pick a task and you start reversing. The code is pretty generous and it's got a lot of strings. So now we can get to something more interesting, is hunting for bugs. The first challenge is setting up an environment, because how do we set up our own cellular network and start doing actual research? Because if we can't do that, it's pointless. And luckily for us, it's not as expensive as it used to be, because I think in the past, basically, an individual could hardly get their hands on a working cellular network. But now we can achieve the same goal by using software-defined radios, or SDRs. So basically, the network stack is implemented in software running on our computer or another embedded device. And the SDR, which is the transceiver itself, you know, just some general purpose transceiver that supports a number of different frequencies. So here are a few SDRs that you guys can try to get your hands on. I mean, they look kind of expensive, but I think they're not compared to what the prices used to be. So I have a Blade RF, and it costs a pretty penny, but it's pretty good, pretty stable, and pretty easy to use. And other good ones are like the USRP B200. It seems to be, USRP devices seem to be the more powerful ones. And by powerful, I don't even know what that means, but basically it's the most popular ones and the most reliable ones. People like to use USRP. Lime SDR is pretty new. They had a crowdsourcing campaign last year and I contributed to that, and I still haven't been able to make it run. So I don't know. And UMTRX is, I have no idea. UMTRX seems to be dedicated for GSM, at least that's what they claim, but it's just too expensive. So I guess once you have the SDR, you need the actual stack that you're going to run on it. And there's a bunch of them out there. Yate BTS is the one I like the most because the code is clean and it's easy to modify. It has good support for the Blade RF, but it only supports GSM and GPRS, and it's easy to compile and run. Actually, it's one of the few stacks that actually compiles, so, you know, it's pretty good. The other one is OpenBTS. It also compiles, and the code is clean, and but it only supports USRP and UMTRX. At least that's the easier ones you're going to be able to run them on, but it goes all the way to 3G. So if you want to do some 3G research, it's a good idea to use the OpenBTS. And another thing is the GSM part of the OpenBTS is they're kind of cheating. You won't see the full implementation in there because they're basically just turning the phone into an internet phone. So they're skipping over a lot of it. So if you really want to do GSM research, it's better to use Yate BTS. These are a few other ones. OpenBSC, that one, I was compiling it was very hard, but it supports also a good number of those SDRs. The code is very clean, and it supports GSM and GPRs. So Open Air Interface and Open LTE are 3G, are both 4G stacks. And to be honest, I was never able to compile them. So I don't know how good they are. So some other things that you want is SIM cards that you can program, or some that are already provisioned, because for 3G and 4G, you can't just connect to any network because there are secrets and there's authentication basically between the phone and the network. So if you want to do 3G or 4G research, I would advise you to get some SIM cards. Also Faraday cage or RF enclosure, because it's illegal to run a cellular network in most countries. So don't do it. Also, another note about SIM cards is that they'll make it easier for you if you have for GSM, at least, if you have a SIM card that you've programmed to match your custom network, it's going to be easier for that phone to connect. So now let's talk about digging into the code. So basically back to picking a task and having a closer look at it. An interesting approach, I guess, my approach when I was looking at this was the following. Basically, I know that layer 3 messages are comprised of information elements. Information elements are basically values, length value, or type length value. So basically, for example, the length value and TLV value messages will contain the length of the message inside, and that makes it interesting because if you got a parser that's relying on the length, we get buffer overflows all over the place. What are different messages? Also, you want to figure out what are the different messages that can be sent to different components. And then you cross-reference those technical standards, remember the ones written by 3GPP. And, that way you know what are the different messages. And then you read the description of those messages and try to figure out which ones have TLVs or LVs. And then you go back to the code and try to identify the parts of the code processing those messages. I mean, a number of bugs you can find this way, to be honest. And I guess let's make it clear with an example. So we saw that there was a CC task that we found when we were iterating over the linked list of tasks. Call control, and it probably stands for call control, that's what we assume. And call control is part of connection management, which is part of the third layer of GSM. And now the question is, what are the different CC messages that we can send? So in the technical standards, we find this, in the technical standards, we find this table, which basically lists all the different messages you can send in the, as call control, in the call control component. And my approach was just to go through each one of them and, you know, identify the contents. But for example, let's look at the progress one, the progress message. The progress message is the following, and we can see there's LV and TLV, and this is actually the paper I was talking about, the talk I was talking about, breaking band. They actually found a bug in the parsing of this message, which was in the progress indicator fields, and that's the bug they talked about in their presentation. And really using this approach, you can find a lot of bugs. So if you want to find bugs today, you should try this. So the problem is that I wanted to take part in pwn2own, and I felt finding bugs like this, it was just too trivial, and I assumed all the other teams would find these bugs. So I wanted to find something, I guess, less trivial. So now I'll describe the mobile pwn2own bug that I used. So I decided to look at GPRS. It wasn't any particular reason, but I just felt it sounded complicated. So I was like, probably the parsers will be pretty bad. So I started by reading the technical standards, and I ended up looking at GPRS session management. So this little graph here is actually part of the earlier one, and it shows the layer 3 of GPRS, and session management is at the very top. It basically, it's there for, since I said it's packet switch, it's there for, you know, establishing connections and then maintaining connections, that kind of stuff. So one of the messages you can send in session management is the activate PDP context accept message. And when I saw this table, I was like, oh man, this looks good, because there's a lot of LVs, TLVs, and stuff like that. And I don't know, it just looks good. So, and then so I decided to look at the SM task, which is also one of the tasks in the linked list. And I assumed it was for session management. Luckily it was. And we find the different handlers by reversing that. And I guess we find one of the handler for that message type. And one part of that message seems to be interesting, is the protocol configuration options. So basically that part is there for, so the protocol configuration options are basically internet protocol related. So you can send information about the network, DNS, and etc. Routers, gateway address and those things. So I don't know if you guys can see this. Is it too small? Maybe. Yeah, I can't see it either. But but basically, this is the code that parses that protocol configuration options field. And I mean, I don't expect you to read all of it, but it looks complicated, right? And the little red box there, if you can see it, is a for loop that basically relies on some fields of our data and just copies to the stack. So I don't know. And to be honest, when I was looking at this, I didn't even know what this field was, but it looks like a CTF challenge where, you know, craft a packet and get a buffer overflow. And it was a stack buffer overflow, so yeah. So actually, yeah, actually it turns out that this is parsing something called the IP control protocol headers. Yeah, that's what I figured out later. So basically, the protocol configuration options are sent by the network. Like I said, you specify parameters, DNS, default gateway. And the problem now is that the phone will never process this activate contact accept message that we want to send in order to trigger this vulnerability, because one thing you'll find is with all this GSM and cellular stuff is a bunch of state machines, and you can't just send any message at any time. The phone needs to be in the correct state before it even processes any of those messages. So the problem for me was that the phone could be made to send this request, made to be in the correct state by actually going on the phone and configuring a access point name, but this is not allowed for pwn2own. So I spent some time reading the standards again, and I figured out that if you send a request PDP context activation, actually all these names are pretty misleading and weird, but that's what they are in the standard. But the network can ask the phone to request a PDP context activation, and at that point the phone will send the activate request, and then the network will send the activate accept message and trigger the bug. So it basically looks like this. Send the request, get the phone to request it, and then accept with the crafted payload. So in order to implement the attack, we need to modify the source code of V8BTS. So I told you it's pretty clean. And actually reading the code helped me a lot in understanding what the messages look like for GSM, for the GSM protocol stack. And for this attack, I'll give you a hint. You need to modify that file, and you can try it. And the exploit itself, I don't think it matters that much, because it's a stack-based buffer overflow, and you get code execution in the baseband. The rest is up to your imagination. What I did for pwn2own was to write, I needed to demonstrate that I actually had code execution. So I just wrote to a file on the file system, and I'll show you in the demo right now what it looks like. Is it on the screen? Is it on the screen? Huh? And now it's all black? Oh, wait. Actually, if you look at the top, you can see, I'm sorry, my font is very small, and I didn't know it was going to be so small on the screen. So basically, this is just, on the right, you have the screen which is connected to ADB. You have a terminal which is connected to ADB on the phone, and on the left is V8BTS running. So let's see what it looks like. So basically, I'm just doing a watch command of the ADB, checking the file system. And as soon as the phone connects, basically nice. All right, let's try it again. Very good. Yeah, so like I said, on the right is a ADB watch command to see if there's anything on the phone's file system. And on the right is V8BTS running. So there you see the file is created over there. Let's see. All right, so I guess that's pretty much the whole talk now. I'll just point out a few things as conclusions. So really, what I wanted to show was that the baseband exploitation isn't that hard. It just looks scary, and there are all these things that people think they should know about cellular networks and stuff like that. But it's really just another CTF challenge. So you really don't need to know much about cellular networks in order to exploit them. And I'm hoping to see a full remote compromise through the baseband, all the way from a cellular network that routes your phone. And there are many targets out there: Huawei, Intel, Qualcomm, and hopefully one of you guys will pwn one of them. And that's it.
Thank you for the great talk. And my question is, were you able to get any sort of debugging capabilities into the baseband chip?
Okay, so I guess the most straightforward way to debug was through the crash dumps. So whenever you crash the phone, you get the RAM dump. You can look at memory. But I guess something I didn't point out was, once in the RAM dump, you get the save state of registers when it crashed. So that's also very useful. So yeah, you can debug every 10 minutes that way. Oh, I guess one thing you can try is through an exploit, you can just try to, implement your own debugger and write to the file system. But yeah, I think that's a lot of work, but it's doable.
So when you exploit, you write to the file system. Has the baseband CPU access to the file system, or do you use exploit to go to the application processor?
Yeah, so the no, I didn't. I don't have exploit to the application processor. The baseband has access to the file system. Basically, there's this thing called non-volatile items, and it basically means the baseband should be able to save permanent configuration options or whatever. So the way they did it was through accessing some portion of the file system on the Android device.
Hi. Well, thank you for the talk. You were talking about the stack-based buffer overflow, and did you mention something about security mitigations for the exploits?
Yeah, so I didn't mention any because there aren't any.
But
So yeah, you shouldn't worry about them. They don't exist in this thing.
because I saw you using like a rope.
Okay, so the ROP chain is because of ARM caching issues. So if I just jumped to some data, it wouldn't have been flushed to the code cache, and basically you start by ROP, copy your shellcode somewhere, and flush the caches, and that's why you need ROP in the beginning at least.
So we are back into the 90s.
To the 90s, yes.
Thank you.
Is there any questions? Well, thank you for the talk.